wire's getting all twisted here. All right, so we'll begin with a word of prayer. Heavenly Father, we thank you for this day, Lord, and I thank you for these students. Just ask you to bless our time together, Lord. In your name I pray. Amen. Well, hopefully my batteries will last. Famous last words. Okay, so is the daily quiz problems. I started with I was trying to save myself some work, and well, you did some of the work for me. It's good. Here's the partial derivatives. Great. And then in the calculation of the determinant down here, so I'll tell you the mistake that was going to propagate and cause you pain. This is supposed to be x rho, I think, and x. Oh, you're doing this one. Oh, well, maybe it's still right then. Let's see here. Okay, yeah. Hey, that's a smart move too. I like that. But this should be this. So the way the determinant works, it goes plus, minus, plus. So this, when you do that expansion, there's a minus. So this is supposed to be plus. And then, so z phi, you've got your x rho, which is cosine. Cosine? What's cosine? Thanks, Dr. Martin. Dr. Martin used to call them cosine and sine. It's like, he calls it cosine. Anyways, z theta. Wait, what? Oh, y theta. Thank you. You got to fight for the right something. I don't know. So here, where are we? Y rho. Y rho. Yeah. And y rho and x theta. We're still on the, yeah. And that's it, because you picked the smart thing to expand on. Thank you. So y rho x theta, which was, hey, yeah, I do believe we have a winner here. So at that point, I'm going to ignore everything you did. Sorry. And not that it was wrong, just it's easier for me. So if you look at this, there's always a rho. There's always a rho. Say rho. So rho squared. Sorry, that was totally unnecessary and somewhat horrible. So you've got a cosine or cosine, depending on how you say cosine. Cosine squared phi for the first term. Then we've got a cosine squared theta, a sine theta, right? And then what? Plus, here we've got ourselves a cosine squared phi. We've got a sine squared theta. We've got a, what else we got? Just a leftover sine phi, right? Okay. It's a little bit disturbing. All right, and then this one here, what do we got? We've got rho, well, the rho squared I factored out, right? Actually, can I be smarter? Is there something common to everything? There should be a sine phi on everything. In fact, these two terms have sine cubed phi. This has sine phi. There's something wrong here. Yes? Which one? Here? Where's that coming from? That is 0. This is supposed to be x phi times y theta, right? Aha! I knew something was wrong, because we should have a common sine phi that factors out, which I know because I've suffered through this before. So with that correction, you notice that there's a sine phi here. There's a sine phi here. There's a sine phi here. So we might as well factor those out since it's everywhere. Right? So there's that common sine phi factor. Let's factor that out, make our life a little bit nicer. All right. So now we've got cosine squared theta, cosine squared phi, right? That's my first term. Now that I've moved that annoying sine phi out front. Then this times this gives me plus, again, a cosine squared phi. But this time what? Sine squared theta. Aha! You see, that's going to be nice in the next step. Over here, what do we got? We factored out the pesky sine theta. We got a cosine squared theta. We've got a sine squared phi again. Over here, we've got plus. We got sine squared theta. We've got sine squared phi. Right? But notice what happens. We've got a common cosine squared and sine squared. These together, factor out the cosine squared phi, that just drops to, yes?
With the cosine squared theta, cosine squared phi, where did the second phi come from, the cosine phi?
Which one are we talking about?
On the cosine phi, where did the second one?
This one?
No, left, that one. Where did that come from?
This cosine phi times that cosine phi, yeah.
Sorry.
It's fine. And then in this term over here, we've got a common sine squared phi, right? So we can factor out sine squared plus cosine squared there, right? So basically this term drops down to what? It just drops down to cosine squared phi, right? This term simplifies to sine squared phi. So lo and behold, we get rho squared sine phi. So in other words, dx, dy, dz, the volume element, the infinitesimal volume element, in spherical coordinates is rho squared sine phi d rho d phi d theta. That is one of the important rules of thumb for changing the measure into spherical coordinates. This is the rule. We will go through this calculation how many times in this course? I hope you're paying attention because this was the time I'm going through it. I will not. I will categorize. If you ask me, but why is this true? I will say no. We already did it. You should have been there. You know? So now we can use this, thankfully. All right? Listen, there's a way of deriving this that's kind of beautiful and maybe somewhat understandable in terms of like little infinitesimal, if you think about little motions. So if you're here and you just go a little bit like that in the dr direction, what's the length of this little line segment? A little line segment, letting r change but fixing the other two things. What's the radius if you're in polar coordinates out to like a little, I mean, how far is that out? The radius is rho sine theta. That's r, right? So actually, I'm not saying, I shouldn't say dr. I should say, this is a movement along what? I'm sorry, theta, I should say. So this is d theta. If I think about it, sweeping a little bit, fixing, just letting theta vary, and I think about the length of the arc, little arc length like that, the little change in length would be rho sine theta, d theta. If I think about the little change in length along the phi direction, something like this, you know. So this would be, you know, along a little d phi. There. Then this time the d phi gives me dl phi. Well, that's the radius here is rho. See, the radius here was rho sine theta because that's r, as we've discussed previously. dl phi, well, that's just rho d phi. And then, of course, if I look at another direction, if I just think about going along like a little radial path, what's the little little change along the radial path? Well, it's just d rho, right? So to find the spherical volume element, dv, I can just calculate dl rho, dl phi, dl theta, and that gives me this times this times this, which gives me rho sine theta, d rho, d phi, d theta. Ah, rho squared, yes, thank you. Keep me honest. As you, right, because these are both angular displacements, so we need to multiply them by the radius in order to get the arc length subtended along those displacements. So yeah, rho squared.
You still have a theta instead of a rho.
Where did I do that?
Well, because you have dv at the top is rho squared sine theta, but at the bottom you have rho squared sine.
Oh, and that's because I'm wrong, right? No, this is good. This is good. This is the kind of question that it makes me feel like I'm not alone in the world, you know? It's good. It's really good. So if you look at this picture where I'm thinking about, you know, making like a little change in, sweeping out a little change in theta, all right? The radius for that arc length, this radius is r, right? This angle is phi, which means geometrically that angle is phi, right? The hypotenuse in this little triangle, which by the way is right angle down here, well, the hypotenuse is rho, and so r is equal to rho sine phi. We've talked about this before, but as you can see, I didn't learn my lesson because I put a theta here where I should have a phi, which is good because now we can correct this and have complete agreement between the Jacobian calculation and the direct geometric infinitesimal argument. Right. Last class, I derived that the area element for polar coordinates was what? RD theta, right? So there, if you calculate dLr, dl theta, what's that? It's dr times rd theta. See, because if you go a little bit like that, well, that dl theta is just equal to the radius times d theta. So you can also derive the area element that I did last time through direct geometric arguments if you start thinking through these things about little infinitesimal sort of triangular regions or solid regions where you're just sweeping out little infinitesimal changes in the coordinates. You can calculate the volume of these little boxes. Assuming, of course, that the coordinates are actually ortholinear. All right. We have that. We will use that. Maybe not today, but now we know. All right. Oh, why did I do this to us? Why? So we have a function f of x, y is equal to x. W is the region bounded above by the paraboloid which opens down, 4 minus x squared minus y squared equal to z. And below by the paraboloid which opens up, x squared plus 3y squared equal to z. One of those is circular, one of those is elliptical, right? So the way they intersect, it's not nice. You know, it's not nice. In contrast, problem 4 over here, guys, is almost the same kind of problem. I say find the volume, essentially. Well, I say do this integral over w, where w is bounded by, well, I said the coordinate planes, and the lower surface was the paraboloid which opens up, and the upper surface is the paraboloid which opens down. Now, these are both circular paraboloids, and they'll actually intersect in a circle which fits in a horizontal plane. This problem 2 is not as nice because this curve of intersection, where did you get it? I don't want to erase because I feel like the answer is here. Okay, I gotta, all right, what I'm gonna do, I'm gonna write some work up here. So the curve of intersection, how to find it? We set z top equal to z bottom. So, ooh, I just erased that. I don't know what that was. I just erased. Anyway, so the top, by my reckoning, is 4 minus x squared minus y squared, whose largest value happens at 4, right? When x and y are both 0, the top curve is at 4. The zenith, the top of that downward opening paraboloid, is at 0, 0, 4. On the other hand, the other one opens from the origin up, right? So its lowest point is 0, 0, 0. And if you think about the graph of the lower surface. But we're looking for where they match up. So we're looking for where their z values match, right? So we're trying to solve that equation. Okay? Well, anyway, that equation describes the curve of their intersection. Okay, so what is that? Let's solve that. What's that give us? That gives us that 4 is equal to 2x squared plus 4y squared. Let's be civilized. This is x squared plus 2y squared equals to, I guess I should just, well, fine, I'll leave it as, let me divide by 4. Divide this by 4, all right? So x squared over 2 plus y squared equals to 1. That's an equation for their curve of intersection, all right? In other words, to find the curve of intersection, you can look at the cylinder which is built from stacking ovals, right? An elliptical cylinder with that equation, that intersects where these two surfaces intersect. And so to set up the integral here, he's done well. So the lower, we do from the lower z to the upper z, right? Any z in this region is got between all right, I think we abandoned that picture, so I can erase it, right? Okay. All right. So, okay, so the point is, if you look at this region, its shadow is all bounded by that curve of intersection, right? That's the largest the shape gets, right? The whole solid fits in this elliptical cylinder, right? So you can say if x, y, z is an element of this solid that we're trying to understand, then certainly we have that x squared over 2 plus y squared is less than or equal to 1. That inequality bounds x and y in the integration region. That's how we have to think about setting up the integral relative to that constraint. We also know that z, right, is specifically between, what was it? 4 minus x squared minus y squared less than or equal to z, less than or equal to, oh, I messed that up. Fine. I'm resisting the urge that I have to reverse the inequalities. That's not helping any of you. Let's see here, less than or equal to z, less than or equal to, if you want to confuse your friends, work with greater than or equals to rather than less than or equal to, just to watch them squirm, but don't do that. Anyway, so this tells us the first thing. This is the innermost bounds, the dz, right? Then these guys here. Now, I disagree with this because you notice I said that we're in the first octant, which means that in here we have x greater than 0 and y greater than 0, right? So we should have, man, that marker is thick. Let's see here, 0, like that. Now, I'm not sure about your upper bounds. I got to think through it for myself. I don't know. So if I think about that oval, right, I'm interested in this part of it, right? So this is equals 1 is that, right? So that gives me y is equal to the square root of 1 minus x squared over 2, right? y is equal to the square root of 1 minus x squared over 2 because we're where y is positive. So that tells me what I should put here. I should go from 0 to, that's your ballpark, but it's not a circle. That's why that's not there, okay? So you're close to the right idea, though. So this should be the square root of 1 minus x squared over 2, all right? And then this may be right also. I'm just making space. Let's see here. So what is this? I mean, so if we take a point in here, x, y, it should be clear that we have 0 less than or equal to the square root. I'm sorry. 0 less than or equal to y less than or equal to the square root of 1 minus x squared over 2, right? How about x? 0 less than or equal to x less than or equal to what? This x, right? What's the max x right there? I think you're right. I think it was square root of 2. Because if I put y equals to 0 up here, I get x squared is equal to 2. So this is actually, yeah, you're right. It's square root of 2. So what I erased didn't need to be erased. Square root of 2 was good there. It's just this inside bound was a little bit fussier than what you had. But that would be it. Yeah. And then I think this looks sort of right.
Well, it had the old bound.
It had the old bound, so it's, yeah. The main point here was setting it up, though. That's the thing that you guys will get stuck on, right? If I had a question like this, I would most likely ask the question in the form, set up the integral. Like, the problem would probably stop right where we got. So what's the main challenge here? The main challenge is really just visualizing the volume, understanding what it is you're dealing with, right? Coming to terms with how you can sculpt that volume from all of R3 by a system of appropriate inequalities. And then how you translate that to bounds. Right? It's tough, right? This one here, I had the top was the paraboloid which opens down, 1 minus x squared minus y squared. And I looked at the plane y equals x as another boundary. And then I said x equal to 0 is another boundary. So after the dust settles, then you've got this sort of slice here, like that, right? And that's the volume you're trying to integrate over. So let's see here how John set up the bounds. The z goes from z equals 0 is down here, right? So that's the down z. This is the up z, is the top, right? So the down z 0 up to the upward z 1 minus x minus y squared. Great. Then I was encouraging, and I encourage all of you, when you do these kinds of problems, you have to come to terms with what's the shadow of the volume onto the xy plane if you're going to set it up like this. The thought process for setting up the other two parts of the integral is essentially the same as our thought process for setting up type 1 or type 2 integrations. It's really the same ball of wax. So the shadow of this thing onto the xy, so first of all, I took the liberty of writing x this way and y this way, rather than trying to make it directly geometrically correspond to that, which would get me into trouble. Because when I think about xy analysis, my x goes this way, my y goes this way. So it's much easier for me to take a second to translate what the shadow looks like from this picture to its corresponding picture in my standard presentation of the xy plane. That's just a point of order for me. If I try to work with analysis on a non-standard written xy plane, I get into trouble, personally. So I know myself. I know writing this picture makes my life easier. So y equals x gives me that. That's one of the edges on the shadow, right? Of course, x equal to 0, that's back here, right? That's this one. And then this, And of course, then there's the other curve from the paraboloid hitting the z equals 0 plane, this piece right here, right, which corresponds to this edge, like that. So type 2 setup is the right way to go here, right? Because you've got a well-defined upper y, lower y, and x ranges from 0 out to this maximum x. How do you figure out this point of intersection? This is where, that point right here is where y is equal to x, and what else? Y is equal to the square root of 1 minus x squared, right? It's where both of those things are true. Or, here's an easier way to think about it. Put y equals to x up in here. That gives you 2x squared equals to 1. So the point of intersection is where x squared is equal to a half. So it's 1 over the square root of 2, which is also known as square root of 2 over 2. Okay, so that's the maximum x. So that's where these bounds came from. See, the y is ranging from x down here, right? We have x less than or equal to y less than or equal to the square root of 1 minus x squared from the picture. And that's why we put these bounds here. And then finally, x ranges from 0 to 1 over root 2, or root 2 over 2. And that's why we set it up like that. And then I freed him of the suffering of trying to calculate the integrals because they're kind of nasty. All right. Again, this is almost the same problem again. I figured if I worked almost the same problem 3 times in a row, it should start to make sense to you guys. I don't know, maybe not. So here we have an upper surface, which is 4 minus x squared minus y squared. We have a lower surface, which is the upward opening usual paraboloid, x squared plus y squared. We're trying to calculate the volume bounded by the upper and lower surface, as well as the coordinate planes. We're in the first octant, where x is greater than 0, y and y is greater than or equal to 0. Okay. Actually, I didn't give z greater than or equal to 0 because that's not necessary. The z is governed by the upper and lower surface, right? I'm just saying, I'm looking at the, so in this picture, it's not this whole shape, right? We're actually just integrating over what part of this shape. So if this is my x and this is my y, we're just looking at this. I can't do it justice. This quarter of it. All right, it's a quarter of this sort of. Have you ever guys seen those like lollipops that have got the weird sort of different shaped top and bottom? They're not quite spherical. They've got, it's kind of like, I don't know, it's kind of like, that's more complicated. I don't know, it's like a quarter of it though. Okay, so again, the z goes from the lower z to the upper z. And then for y and x, we have to come to terms with what's the curve of intersection. What's the curve of intersection here? That's what this calculation is about right here, right? Curve of intersection comes from where the z's are equal, right? So that's where x squared plus y squared is equal to 4 minus x squared minus y squared, which of course gives us 2x squared plus 2y squared equals to 4, which is happily this guy, right? The circle of radius root 2. So if I was to draw, here's y, here's x, the shadow, we've got root 2, and this is the shadow onto the xy plane that this volume casts, right? If you were to form a cylinder, which was this shape stacked up forever and ever in the z, the volume would completely fit within this sort of, the volume fits within this quarter circular cylinder, if you will. This shape the volume sits inside this thing, right? The shadow, I mean, specifically, it's, God, I don't know, I can't. I mean, it fits in there. So I have to bound x and y according to that, that shape. And so, like he's told me, 0 is less than y less than the square root of 2 minus x squared. Great. And the x ranges from 0 to 2. So this is, yeah, that's a legitimate setup for this integration. Yeah.
So we care about the intersection, curve of intersection, because they're two paraboloids.
Right. And we could have, I mean, this example, the set of examples is focused on paraboloids, but you could look at the curve of intersection of a plane and a paraboloid. Right? You could have something like here, let's look at that actually. I have not left myself sufficient time to derive the change of variables theorem today. My apologies, you guys. I'm just going to have to work another example of change of variables before I get to the proof of the theorem. You'll forgive me, yeah? But what I'm trying to do next is actually combine the concept of these examples with a change of variables theorem. Okay? Yeah.
Dr. Real quick with problem 4.
Uh-huh.
Could that have been solved by changing it to polar coordinates? By saying x squared and y squared equals
Cylindrical coordinates, but yeah.
Okay.
Actually, maybe I should do that. Maybe I should actually solve problem 4 using a change to cylindrical coordinates. Okay? Let me show how that's done. It's a good idea.
Why would it be cylindrical instead of?
It's a triple integral.
Oh, yeah.
I mean, if you already did the z integral, and then you're just working on x and y, then you could look at that as a polar coordinate change. You're not really wrong. I mean, the difference between changing to polar coordinates and changing to cylindrical coordinates is really not so severe. It's really the same calculation, just reorganized a little bit. So I don't really deeply disagree with you, Josh. All right, let me try this again. First, yeah.
Are you taking tennis today?
Yeah.
You already did? Oh, he did take it. I thought I was going to get some points there. I did think on that. I don't know what I'm thinking. I was 100% sure I was about to get a
See, that illustrates the fact that these problems I'm showing you guys, trying to walk you through today, these are difficult problems. To me, this is as hard as this course gets. Working these integrals with the complicated, somewhat complicated intersections that maybe are not readily visible. Sometimes these problems will come with a picture in a book or something, right? So they kind of give you a sense of where things intersect and how they're related. But in lieu of that picture, these are very hard problems. I really think this is about the hardest the course gets, in my personal opinion, because I mean, we don't all have this ability to visualize 3 dimensions. And it's not just that, right? First of all, you need to be able to visualize 3 dimensions. You also need to be able to see through equations and understand what that equation means geometrically, right? Like that's a non-event for me. I see z equals x squared plus y squared. I know immediately in my mind's eye what that is. I know that's the paraboloid which opens up, right? I see 4 minus x squared minus y squared. It doesn't take me mental energy to know that that's a paraboloid that opens down, right? I've done nothing but math my entire adult life. All right? So I have a certain advantage over you guys. You are learning. So when you see that, there's probably some amount of time that transpires between you looking at the equation and realizing geometrically that's what that is, right? If that time is larger than 75 minutes, then you're in a lot of trouble, right? I'm just saying. Sorry, I digress. So the shape I was looking at, I'll write it this way. It's x, y, z, such that if we really get down to it, it was this. It was x squared plus y squared less than or equal to z, less than or equal to what? 4 minus x squared minus y squared. Was that not it? And also x greater than or equal to 0, y greater than or equal to 0. This set of inequalities fixes the w, the volume that we were studying in problem 4. All right? That's what the volume is. And so I can draw a picture of that. I can try. And so, you know, where do these guys intersect? We said what z does that happen at? Right, thank you. That was actually not a hard question. The rest of you should be like, oh, I could have said that. It was sitting right here, right? So it's where both of these surfaces are intersecting. That's where both equations are true, right? So z is equal to aka at z equals to 2. Now, I could not say that for the problem that just erased that intersected along the elliptical cylinder. They did not intersect at the same z. The curve of intersection kind of like, it depends on z. It's not a planar curve. But the curve of intersection here is actually a circle for what it's worth. All right, so here's a sketch, if you will, of the volume we're trying to integrate over. And so my question then is pretty simple. Can you describe this volume in terms of cylindrical coordinates? How would you do it? How would we describe cylindrical coordinates? What are cylindrical coordinates? Do you guys remember? R, theta, and z, right. I introduced these early in the course, not because we really have used them much up until now. The reason I did that is sneaky. It's very simple, actually. I wanted you to think about it a little bit. I wanted it to sink into your brain and let it stew there for a while. So now that we're talking about them and actually going to use them, you've actually already kind of at least had it on your brain for a while, right? Another way to teach this course is to introduce cylindrical coordinates at this point in the course. I don't think that's friendly, because you guys are in the midst of other thinking, which is very non-trivial, namely these examples, right? So it's nice to already have some familiarity with that. I hope you understand that's why I didn't test you on it earlier. It's not because it didn't matter, it's because it wasn't the point of earlier. Okay, anyway, educational philosophy aside, can you tell me? How about this? I'll do the easy thing for you. This translates into spherical, cylindrical coordinates as r squared less than or equal to z less than or equal to 4 minus r squared. This is star in cylindricals. You notice that I'll just skip some letters here, there. That's the inequality in cylindrical coordinates. So I guess that pins down z. So how would you describe r and theta? It would be 0 less than or equal to r, less than or equal to something. 0 less than or equal to theta, less than or equal to something. You know, theta equal to a constant, those are half planes, right? So here's a couple pictures. This theta equals theta naught. That's what that looks like. Theta equals to theta naught is a half plane. It's the collection of all points that go off to the theta naught direction. What's r equals to r naught? I mean, r equals to a constant, that's a cylinder. Hence the name cylindrical coordinates. Why are they called spherical coordinates? Is because if we set the spherical radius equal to a constant, we get spheres. We set the cylindrical radius to a constant, we get cylinders. So it's cylindrical coordinates. So guys, care to tell me? How about theta? Can you tell me what? I mean, this is theta equals to 0 here, right? So you're starting at theta equal to 0. That's this. This is theta equals 0 is the back. This piece of it, you know. Yeah, pi over 2. So we swing over to here until we get to that back half of it, which that's the back half. The back half, theta equals to pi over 2. Yeah. So how about the r? 2, right. Is that right? Oh, almost right. That's r squared. This is r squared. Your idea is right, but you got to just square root of 2. Now, we need the change of variables theorem. What's dv? What do you guys think dv is in polars, like cylindrical coordinates? We go, actually, so we're looking, how do we change dx, dy, dz into polar coordinates? If you want to think of it in a heuristic sense, it's just changing that. And maybe we'll derive it next class, but it actually is simply r dr d theta dz, which you can get from multiplying like the dlr times dl theta times dlz in the sense I was talking about earlier. We could derive it with the Jacobian calculation next time, fine. Anyway, the point is that's my dv, so we want to integrate. What are we integrating over this space w? What was our function? Z, right? The function z, which is kind of I mean, that's not a very exciting function to integrate. I'd sort of rather, could I integrate something more interesting than that? Let me make this problem more interesting, if you don't mind. I'd like to trade that z for an x. That would actually be more instructive for you guys. Okay? So let me actually modify problem 4 a little bit. Let me make this an x instead of a z, because then this integral, actually, the process of applying the change of variables theorem is actually a little bit more substantive. Because if I start with z, how do you change z to cylindrical coordinates? Right, so you wouldn't learn anything there. But if we start with x, and we change this integral to the cylindrical equivalent by the change of variables theorem, well, that's actually a little bit more to it. Okay, so we go from 0 to I'll say 0 to the square root of 2, integral from 0 to pi over 2. Integral from, now this is the interesting one, r squared up to 4 minus r squared. All right. Now what is x in terms of, how does x related to r and theta? R cosine theta, very good. So x is r cosine theta. So what I've done at this point, remember what I said at the start of all this? It's just like U substitution. We have 3 things we have to change: the bounds, the integrand, and the measure. The bounds are by far the most complicated part. Much more so now than in Calculus 1. The measure, it's not too bad. It's just r dr d theta dz. I got to be careful, though. The ordering of the differentials has to match the bounds, right? So, yeah, there's an r. Which comes first, though? Does dr come first? right? Because I've got z bounds here, right? So I go dz, then d theta, then dr, with the way I just set it up. So let's see your integral from 0 to root 2, integral from 0 to pi over 2, and let's see here. So we're going to get an r squared cosine theta, and then z evaluated from z equals to r squared to z equals to 4 minus r squared. Then you got yourself a d theta, and you got yourself a dr. See what I just did the z integral. What's the integral of z? I mean, we have dz. Integrates to z, that's it. So the integration over z wasn't that bad, actually. Now let's clean it up a bit. This is the integral from 0 to the square root of 2, integral from 0 to pi over 2 of r squared cosine theta times, what is that? That's really 4 minus 2r squared, is it not? D theta dr, which is equal to the integral from 0 to square root of 2, integral from 0 to pi over 2 of, let's see here, 4r squared cosine theta. Oh, I'm an idiot. I should use an important calculational simplification here. It's important to emphasize to you guys, when we can do it, we should do it. It makes our life a lot easier. It helps us not make mistakes if we do it properly. So it's a good habit to get into when you see it and it can be done. We have rectangular bounds. What I mean by that is that the bounds are not dependent on one another, right? They're not intertwangled, to use a technical term. Okay, it's not actually a word, but anyway, you notice you got like function of r, right? And you've got a function of theta. So there's a you can factor the integrand. Function of r times function of theta. When you actually go through the process of iterating these integrals, it's going to be the same as if you just multiply the integrals here. So this is in fact the same as the integral from 0 to root 2 of, well, 4r squared minus 2r to the 4th dr, and then times the integral from 0 to pi over 2 of cosine theta d theta. This is a little lemma that I find very convenient to use when it's appropriate. When is it inappropriate? If your bounds are dependent one on another, you can't do this. Or if you can't nicely factor the integrand. I mean, there are times when you can't do this, but so we get 4/3 times the square root of 2 cubed minus 2/5 times the square root of 2 to the 5th power. All of that times 1. My brother says this is an important thing to notice. You talk about sine, right? Or, let's see here. Well, in this case, we're talking about cosine, right? So what's the area under like a quarter of the graph? Do you guys know? I mean, I can work it out in this case. We get minus sine theta, right? Evaluated from 0 to pi over 2, which is what? Oh, I'm an idiot. What's the integral of cosine? Sine. Yeah. Like, wow, I'm getting a negative area. That's weird. So that evaluates to 1. The area under that little lobe of cosine is just 1. And so there you go. That's the answer. I assure you that is way easier than if we were to try to do it in Cartesians with the square roots and all that junk, right? So, sorry, I was going to do the plane intersecting the hyperbola, but we'll, you know, not hyperbola, but paraboloid. We'll do that soon. So, thanks, guys.